Alright, I guess we'll just make this one a quickie.
Welcome to iLecture Online, and here's a new topic for discussion called conservation of energy.
While I'm chewing on it.
And so what I'm going to show you here is a really interesting, straightforward, easy to apply method to solve a lot of energy problems.
Things like soldiers.
And the concept
do
is
our quick base.
rather
We're not going to go
simple.
all the way back. So
What we can say is that, for example, we take a snapshot
I need to be down
of
here
an object
and
that
be
has
where this
potentially
accelerating
mass
frame,
m,
him,
that will be in
is
some
to
position,
be
maybe
in
some
this.
height
You might be
above the
looking at
ground
it now.
with some initial
Whoever's
velocity,
looking
and
at
maybe
this
some
now.
forces pushing it. So this is the initial state of the object, and then some time later, the object will be in a different state, and we'll call that the final state, where it will be perhaps
Okay,
at a
you're
different
not
height,
ADP hard
perhaps it
enough.
will have a different
That is the
velocity,
slope.
and perhaps in
At
the
point A to
process of
point
going
B,
from
you
state 1 to
graph
state
like you
2,
could
or
throw more.
initial
You
to
with
final state,
actions, its
it
spooky
had to
distance is a bit
overcome
better.
some
But we'll
frictional
get into
wind
that. We'll get
resistance.
wind to Y, the
So
fractal
how do you set up an
looks the way it
equation
does.
to relate those initial and final
It's
states
an adult
to each
dumb
other?
question.
What
Sounds
you
like
can
he's
always
cheating
say is
on
that
you,
energy is
or
always conserved.
he's lying to
Therefore,
you,
we
one of
can
the
say
two.
that energy initial must
Zebra in
equal
hand,
energy
working the master
final.
key. We are
So,
doing
what are the
conservation
types of
information.
energies that this
I
object
usually
can have?
like
Well,
function
it
of
can
the
have potential
dominion,
energy, and it can have kinetic
or
energy. So
solving a
the initial energy
exponent
that
with
it
a
has in
logarithm.
this state right here
Logarithm,
means that it has some
exponent,
initial potential
exponent, or
energy
logarithm,
and some
exponent.
initial kinetic
What do you mean?
energy.
Well,
So that would
there's
be the total
part
energy
7.
the object can have.
Idealization
It's the
is
sum
the
of its potential and
is
kinetic
the seventh
energy.
part, but
And in
obviously the
final
most important,
state,
according
when
to
it
their
has different
rules,
height
right hand,
above ground and a different
on what
velocity,
F is.
you will
So,
have a final total energy
when
or
all the parts of
final
this exam
potential
have
energy
to equal an answer.
and
If you were
kinetic
teaching
energy.
physics in the zeros and ones,
However, that's not the total picture, because we could also, while it's transitioning from initial to final position,
we're getting there.
it can also be subjected to a force. Somebody could be doing work on the object, and of course, if you're doing work on the object,
Maybe
you're
not.
adding energy
Anyways, this is
to
a
it.
simple little
So that
metric. So
means
basically
we
what
could
we've
also
done
have
here
additional
is
energy
this.
available because work was
It's
done on the
the
system.
parts
So we have
that
to add to
equal
that
the
any
final
potential
exam.
work that was
I
done on the
gave you
system. So
parts
we will have
that
not
would
just
be
the
good
energy that
for
it started
these
with,
scales,
but additional energy that was
these
given to it
additional
in the
energies in the
process by
fields
time it
of
gets
feet
to
per
the other
second,
side.
meters per second.
So,
Feet per second,
that
centimeters
means
and
that
inches
it
on
could have potential,
the
have more
log is
potential
half
energy
that
or
time.
more
If
kinetic
it takes
energy
you
or
that
both,
long to
simply
run a
because
mile,
work was put
6
into the
minutes,
system and more
or
energy
excuse me,
was
running a
added.
6-minute mile,
But then, of course,
you're
we sometimes
running,
have to
hold on,
overcome
I'll tell you here.
friction, which means
In an
that
easy
energy
fixed
could
breakdown,
be
6
lost
miles
in
per hour,
overcoming
what,
friction. So some of the work that we put into it, or some of the potential kinetic energy
10
the
feet
object
per
had
second, or 10
initially
miles an hour,
could have
something
been
like that,
used to
and it takes you
overcoming that
10
friction.
at
So
10
we
miles an
have to
hour,
account
6
for that
minutes,
friction on
8
the
miles
other
an
side of
hour,
the equation.
7.5
So we say
minutes.
plus
I think that's 8
energy
minutes for
lost
6.
due to
And
overcoming
those
friction.
numbers, always, they'll do
Which
it. They do
means,
it all the time in a
think
lot of
about it,
different ways.
if all the work that
They're
we
doing
put
it
into
here
it was
now.
used to
We're
overcome
doing
friction,
feet per
and let's
second
say that the
to
amount was just enough, that means
miles
that
per
the sum of
hour,
the potential
but
kinetic
different.
energy initially
Now
will
we're
not
doing
have to change.
5.
It will be
We're
the
still
same
keeping
as the sum it has over
0.5
there.
miles an hour.
If the work we put into
Equals
the
feet
system
per
was
second,
greater
miles
than
per
the energy
hour,
lost, then
feet per
these two
second
will be
to
greater than those
miles
two
a
combined.
minute,
And if the
or
work
minute
put into the
miles,
system
not
was less than the energy lost
miles
over
per
here,
hour.
then of course more
So
energy
those
was
simple
lost, and
triangulations
that
are
means
enough
that
to
the
just
total sum of
wreck
these two would
your
be less
face
than the total
equation
sum of
because
those
it's
two.
happening here.
And that's kind of the way to
And
look at
log
it. So this
0.5 or
equation right
0.1,
here
if this
is
was
the
1, it would be 2,
all-inclusive
3,
equation
4,
that
1
we'll
to
be able
4
solve just
would
about
get us
any
that system. Here I'm
conservation of
keeping
energy
this
problem.
at 2 to
And I'm
3
going to show
or
you
1 to
a whole
3
bunch of
because
examples
in thirds,
by using this equation. Now, it turns
99.9,
out that
plenty
we don't
enough for
always
me.
have work
It
put
will
into
fit
the system.
in the
We don't always
square
have energy
without
lost.
running,
We may
squishing
have
out.
zero potential energy
In the
initially if
Gaussian,
it starts off from the ground, or it may
here,
have zero potential energy
we know
when
that
it ends
that
on
would
the
be
ground.
center
Or maybe
mass
when it starts out, it's not moving,
because
or when it's finished,
geometry
it's not moving. So you
triggered
can
that
see
plate
that
in such a way.
all those terms are available
However,
in the
that
initial
starts the
equation,
spectrum
but then
down.
when
Now,
you look
again,
at
we'll
the
get into
situation, you have to adapt it,
feet per
or things
second
are a little bit
at a
different.
football field.
So anyway, that's your
And
basic
bullets and
introduction
arrows
to how to
that do this
utilize
as well. Their
this equation to
scale
solve
is
energy
still
problems.
physics,
Now, or
but on
energy
the black body
conservation problems.
problem,
So now let's
Maxwell,
go
Ray
look
Light,
at
and
these next
genes,
videos coming up and see how
some
we
other
actually
stuff
do
we got
so.
going on here. Cool beans. That's the slope.